So in this video, I'm just going to quickly go over how to respond to certain data test questions. I've sort of completed some of the easier ones already, like finding an average and determining the absolute uncertainty of the mean. Those questions tend to turn up on data tests. The first sort of challenge comes up here where I'm asked to find or identify the relationship between height and time squared. I just want to note this time squared here is already calculated for us. So not all data sets will do this. Sometimes you'll have time and you'll have to identify a relationship between height and time, and that would involve finding or identifying that it is a squared relationship. Here I'm going to treat time squared as if it's on our x-axis. On our y-axis. And the method I use is pretty robust in terms of finding ratios, but it's going to look a little ludicrous in this case. The benefit of it is that we'll be able to do it in all data sets in the future. So the first thing we're going to do is create a table of values with my heights, which start at 0.5 and increase by 0.5. And time squared, which is already processed here, and I've already answered question 1 for my 2 marks. So 0.107, 0.233, 0.303, 0.407, and 0.510. Just be careful entering these in. Make sure that you don't make any transcription errors that might lead to a mistake, because it can make finding this relationship a bit more difficult. So I can see that as height increases, my average time squared also increases. That's these values here. Because of that, I don't need to look at any sort of inverse relationship. I know that it's going to be proportional or proportional squared. So if s is proportional to t squared, which is our dependent variable, we could say that s is equal to k t squared, or s over t squared is some constant. I'm going to take that, and that's going to be my first column here. K is equal to s on t squared. And because in physics we would usually check our dependent variable squared as well, this is where I said I mentioned it's kind of nonsense, because we would never have to check for t to the power of 4. But it's useful, because if this was just time, we would identify here that our relationship is proportional between s and t squared. So to find these ratios, I'm going to take my s and divide by my t squared. 0.5 divided by 0.107, which gives me 4.67. Don't worry too much about significant figures here. And I also need to be aware of that squared. That's my next column over here, which is 43.67. And I'm just going to quickly process the rest of that data. Alright, I've pumped them into my calculator on the right, and you can see that clearly the relationship that's most appropriate here is our relationship between s and t squared, which is, again, in this kind of contrived example, it's the linear one that we're checking. It's fully expected, but I just want you to be aware of that trick, that sometimes you need to really read the units or read the labels on our tables to make sure we know exactly what's going on. So I would get 1 mark for utilizing all of this data. I'm just going to put that tick over here, 1 mark for utilizing all of that data, and I would give myself 1 mark for saying that s is proportional to t squared. It hasn't asked for the mathematical relationship here, so that proportionality statement is fine. The next question asks us to use that to predict how long it will take for the ball to fall 5 meters. Now, it's not a perfect system, but rather than graphing it all and coming up with a regression, we can find our average constant proportionality here and use that to determine the gradient, or an approximation for the gradient of this graph. 4.67. I'm just typing that in the calculator on the right here. And let's divide all of that by 5. So 4.74. So if S is proportional to t squared, we can say that S is about equal to 4.744 t squared. Way too many significant figures, but that's not one of the assessment objectives here. And it's going to fall 5 meters. So t will be equal to the square root of 5 over 4.7, which is 1.03 seconds. Let's just do a little sense check. Taking that back to the other page. 5 meters is about double this height of 2.5 meters, so our time should be about double, 0.5 seconds. We're on the right track. The next type of data set that we could get is either a linearized or unlinearized graph. Now again, I've already filled out the easy question here, just identifying the force when the distance between these spheres is 0.2 meters. Simple reading of the graph. Zooming in and out, making you sick. All right. A more difficult question here. If it's a linear graph, you just find the gradient, you find the intercept, and you approximate sort of a line of best fit. But when we've got a squared relationship, or in this case, what probably should be an inverse squared relationship using our law of universal gravitation, that should be capitalized. What I'm going to do is I'm going to create another table of values, and this time I'm going to plot f against r squared and determine that k of, sorry, it should be inverse squared, so 1 on r squared. So k will equal f over 1 on r squared, or if we can really simplify this, k will equal fr squared. So the first thing, let's get all these values into a table. Okay, I've plugged all the values in. Just on the right of my screen here, you can see where I've used my calculator to determine what f over 1 on r squared is. You can see that that k is constant. Like, there's a little bit of variation here, which is to be expected given sort of the resolution we read it off the graph with, but it's clearly an inverse squared relationship between f and r. So f is proportional to 1 on r squared, or we could say that force is equal to 0.001 times 1 on r squared. Now, it hasn't asked me for any uncertainties here. There's no error bars in the data. It's not linearized. There's no max or min lines. This would be enough to get full marks here. Now, it's 2 marker, 1 for the relationship, 1 for the use of data. I just want to note here that it's really, really common for students to forget that they have taken the inverse square relationship here. You've done all this work, don't slip up at the last stage. It's handy that we found that gradient, because now we can extrapolate the data to determine the magnitude of the force when the distance between the spheres is 0.1 meters. I'm just going to use my equation. So 1 mark here for just using the data. My second mark is for appropriately substituting and my final mark is for the answer. Times 1 over 0.1 squared, which is 0.1 newtons. Now again, this is a pretty contrived experiment, just to come up with some good types of data to analyse. It's not very realistic. Don't know how you'd find a couple of 3,000 kilogram spheres that you could separate by a millimetre and actually collect that data effectively. All right, the last kind of data set we can get is one of these that we'd sort of expect you to produce for your IA2. It's a linearized graph with max and min lines. I've included a formula here that's not in the formula book, so that's probably going to be relevant. I can also note that our initial velocity has been given. So the first thing to do here, it's asked us to identify the approximate average value for the range when the launch angle is 45 degrees. So I need to know that sine of 2 theta is equal to sine of 90, which is equal to 1. So I'm looking here at this data point here, and I can see it's about 22.5 or 22.6. So my range is about 22, let's say 0.5 meters, but there's some uncertainty there given by the error bars. I can see that it extends all the way up to 23 and down about a third, leaving about a third to 22. So probably more precisely to say that's 22.7 plus or minus 0.3 meters. And again, I've just done that visually. 1 mark for each of those. The next question has asked me to organise evidence from the dataset to identify the relationship between launch angle and horizontal range, including the uncertainty of the gradient and the y-intercept. So I'm going to start with my range, let's call it S of x, and that's going to be equal to some gradient with uncertainty times my x-axis, which is sine of 2 theta, plus, and this is bad exam technique, but there'll be some y-intercept. And I've gone outside my working box here. The gradient and intercept I'm just going to grab from the best fit. So 21.037, I'll just write it over in my calculator so I don't forget it. And 1.5635 is my y-intercept. So 21.037 and positive 1.5635. A really common error is keeping this as positive if perhaps that best fit y-intercept was, or the middle y-intercept was negative. So just be really conscious of that. All right, let's calculate my uncertainty of the gradient. It's going to be equal to the maximum gradient minus the minimum gradient all over 2. My maximum gradient, working on my calculator on the right, is 26.302. My minimum is 17.174 all over 2. I'm making sure to show that working to get full marks. And that goes right up here in my gradient. My uncertainty in the y-intercept, it's the same working out, just with the maximum and minimum y-intercept. So I've got my biggest y-intercept is this one here, 5.1725, and I'm subtracting a negative number, negative 3.3153, and it's all over 2. All right, so I'd get 1 mark for my intercepts uncertainty, 1 mark for my gradients uncertainty, and 1 mark when I make sure that my equation is in terms of range and sine of 2 theta. So let's deduce the value of acceleration due to gravity and the percentage uncertainty in that value. The first thing I need to do is go back to this formula. I'm going to need to take this. So S of x is equal to u squared on g times sine of 2 theta. Now u squared is given, u is 15. G is what we're trying to figure out here. The only thing with uncertainty is is our gradient. So if I was to take this equation here, S of x is equal to 21.035 times sine of 2 theta. You can see that these two statements should be the same. So u squared on g is 21.035, or u squared on 21.035 is g. Over on my calculator on the right, 15 squared divided by 21.035 gives me g equals 10.7. Now my uncertainty in g, or my percentage uncertainty in g, is just equal to my percentage uncertainty in the gradient, which is 4.564, which is my uncertainty in the gradient, divided by my gradient for my line of best fit, 0.35. Over on my calculator again, 4.564 divided by 21.035, which is about 22%. So I can say that G is 10.7 plus or minus 22%. And now let's see how valid that is. Let's use our percentage error formula, which will be 10.7 minus 9.8 all over 9.8. Which is 9%. So I'd say the approximation is reasonably valid. And most schools use sort of a plus or minus 10% for our, it's valid if it's within 10%. Just consult with your teacher to make sure you're in line with what they want. So I apologise for the quiet volume of this. I'll try to edit it up a little bit, but I've been trying to sort this one out at work today. Best of luck with your upcoming data tests.